Welcome back to another AP Physics 1 topic overview. Today we're going to be talking about the modified Atwood machine, otherwise known as two-body problems. So let's get right into it. Let's start off here with our facts. As always, the facts are going to be in the description down below, along with the exercise that we are going to do here today. Newton's second law, really the main idea that I'm going to talk about here is just my equation. And with this unbalanced forces equals F net equals ma, I'm going to get a little bit deeper into this on the next slide. Just know that when I'm talking about unbalanced forces, it's the same exact thing as the net force. So let's move into our other facts. So taking a look at solving problems with forces, same exact thing here with Newton's second law. The first thing we're going to end up doing here is drawing the free body diagram, and that's just a part of the question already. You should always do that even if they don't ask you to. It's a really good practice. You're going to need it anyways to create your equations in step 2 here. You're going to write two equations, one for Newton's second law in each direction. So up forces minus down forces equal ma, left forces minus right forces equal ma. You don't need to create an equation in a direction that there is no acceleration in. So say that the object is not moving up or down, you don't need up or down forces, or up minus down forces equal ma then. If you're only moving left or right and accelerating that direction, then you'll just do left forces minus right forces equal to ma. Just below that, I have the equation again there, unbalanced F equals F net, then equals ma, just to show that that left forces minus right forces is the same thing as my unbalanced force or my net force. Note here, we are always going to kind of avoid negatives here, so we're going to start my equations in the direction of acceleration. So if my acceleration is, say I'm going up and down, and my acceleration is downwards, instead of doing up minus down forces, I'm going to do down minus up forces equal ma. So let's move into the last page of our facts. Alright, so two-body problems. What we're doing in a two-body problem is draw a free body diagram for each object. Then we're going to set up our Newton's second law equation for each object separately. And I have this set up in the example, as you can see if you've looked at the Google Doc. Acceleration is the same for each object. This should kind of make sense. It's one system moving together. I'm going to have a GIF of what this looks like on the next slide. So they should both gain the same amount of speed each second because they're moving as one object. What we're going to have for these ones as well is if there's one rope, there's one tension, or one strain, one tension. So if there's one strain between two blocks, we have the same tension throughout that entire strain. On the bottom here, acceleration, this is going to be important when setting up our Newton's second law equations. So if we have here an object increases speed, its acceleration is in the direction of motion. If we're decreasing speed, the acceleration is in the opposite direction of motion. So let's now see what our example is going to look like. Alright, so taking a look at our example here. We have a mass of 0.3 kilograms, hangs off a lab table attached to a pulley of negligible mass. That just means that we're not really worried about rotation ideas. We'll get to that later in the school year. While a 0.25 kilogram lab cart is held at rest on a frictionless track. So like a Pasco track, what we have in our class is the Pasco cars on the Pasco track. That's a frictionless system. Same exact idea if you have a veneer cart on a veneer track as well. So the system is then released, allowing the hand mass to fall as the cart moves down the track. So this GIF comes from a simulation I was able to find online. So you can actually test this out for yourself when we make the calculations. If you'd like, I'm going to link that in a pinned comment in the comment section down below. The only difference between this simulation and what we're going to do is it seems like they use 9.8 for gravitational field strength or acceleration due to gravity instead of us using 10. So if you just want to check that out, just make that change when doing your calculations. Otherwise, then you can see that physics does indeed work for this. But what we see here is once the cart is released, it moves to the right and it increases speed until it hits into the bumper. And then you see the hanging mass there. It ends up moving downwards while increasing speed. So this is going to be important when we make our Newton's second law equations later and talking about direction of acceleration. So let's now move straight into our example. Alright, so just a reminder, if you happen to skip to this part of the video, you should kind of go back to the last chapter before this because it will show the actual system in movement that I had with a GIF of this setup that I am explaining here. So you actually want to see how the objects are increasing speed and what direction they are moving in. And again, that's in the chapters in the timeline below. Also, this example and the fact sheet are in the description down below so you can follow along or move ahead and see if you get the things correct. So here in part A, we're just going to draw a free body diagram of the cart after it is released. So again, it's a frictionless track, so we know there's no friction here against me. So for this, the cart, what I'm going to have here first is the force I'm always going to have on Earth, which is going to be Fg, and that is straight downwards, and Fg is the force, let me fix that, it's going to be the force of Earth, again, so it's the object on object, so force of Earth on the cart. Alright, so now the rest of the forces have to be contact forces. Fg is my only non-contact force in AP Physics 1, so everything has to be in contact with this mass. So if I look at it on the table here or on the track as it goes down there, what we're going to end up having here is my normal force pushing straight upwards. So that is going to be perpendicular to the surface. Of course, that's what the normal force is. That's going to be Fn. And we have here Fn is the force, and it's not a track. So we have force of track on cart. It's like a Pasco track, one of those, or a veneer track, whatever you have in your classroom. That's what the cart is on, and that's frictionless if you have the Pasco cart on the Pasco track. Same thing with the veneer cart on the veneer track. It's a very low friction or frictionless system there. So what is attached? What else is attached to the cart? What else is in contact with the cart? My bad. What we have here is a string, and that is pulling it to the right, as we saw in the GIF from the previous slide. So we're going to have here Ft, and Ft is going to be the force of the string or force of string on the cart. Alright, so that should be everything that we have here because we have a frictionless system, so we don't have friction going against the cart. What we're going to end up having in contact with it is the track pushing up on it and the string pulling it along to the right. So now we can look at that hanging mass in part B. Alright, so I'm looking at part B. We're going to consider the hanging mass after it is released. Draw a free body diagram of it during this time. So again, we're going to start off with my force of gravity or the force of Earth on the object, and that is of course going to be straight down on Earth. So we're going to have here again that Fg is the force of Earth on the hanging mass. Alright, so the rest of the forces have to be contact forces. So the only thing in contact with this mass is a string, and that is pulling it upwards. And again, I'm going to call this Ft, and that is going to be the force of the string on the hanging mass. Alright, so this will be my only two forces on the hanging mass because I have my non-contact force, which is Fg, and the rest of the forces have to be in contact with the object in order to provide that force, and the only thing in contact with that mass is the strain, and that is pulling upwards. Alright, so let's move into part C of this example. Alright, so for these two parts, we're really going to break down the entire motion of the system. So again, if you want to go back and look back at the GIF in the chapters there and see how the system is moving, this is how we're going to create our Newton's second law equations. So I know this might seem really long and we can maybe just get straight into it, you're thinking, but you want to really break down everything. The Atwood machine, or the modified Atwood machine, is a very important idea. It comes up a lot on the part 2s or the FRQs of the AP Physics 1 exam, and you kind of want to have this down. This is pretty much the culmination of everything that we've done for the first few months of the class. So looking at the cart here, going back to the GIF, it was moving to the right and it was increasing speed. So what we're going to have here is direction of the cart's motion, and we're just going to put here to the right, and I'm just going to circle increasing just to make my life easier here. So it was moving to the right while increasing speed. So we're going to first now explain what is happening based on our facts of physics. That's why I included the acceleration facts for motion, or kinematics, and not just the direction of acceleration based on forces that are unbalanced. You could certainly do it based on forces that are unbalanced, because we look at Ft, there's nothing against that as it accelerates to the right. So you can talk about just forces for the direction of acceleration. I'm going to break this down by motion here, and then worry about forces later when we actually use Newton's second law. So the fact that I'm going to end up starting off with is that when I have an object that increases speed, its acceleration is in the direction of motion. And that is going to be my evidence here. So again, we do our evidence, reason, and claim to fully explain everything. So when an object increases speed, its acceleration is in the direction of motion. So that is my evidence to get my direction of acceleration. Then my reasoning is going to be that since the cart is moving to the right while increasing speed, this is important to explain both of these things. If for some reason on an AP exam you had to explain the direction of acceleration for an object, you want to explain everything so you're as thorough as possible when communicating your ideas of physics. So this is going to be my reasoning here. And we're going to have here, since the cart is moving to the right while increasing speed, we can then make our claim. We know that when an object increases speed, its acceleration is in the direction of motion, and we're moving to the right while increasing speed. So we can make the claim that my acceleration for the cart is to the right. So the cart's acceleration is directed to the right. So we can then put that in here as well. And now this is going to help us in order to make our Newton's second law equation for the cart as it moves down the track. We're going to start with the force to the right. There's no force to the left anyways. And then do right minus left equal to ma. So now we're going to look at part D, which is going to focus on the acceleration of the hanging mass. So let's move into that. All right, so now moving into part D, we're looking at the acceleration of the hanging mass. So going back to the GIF that we had earlier, again, if we want to look at that, it's in the timeline of the video in the chapters. You can see that the mass was moving downwards. So we can just have here that this direction of motion is going to be down. Then, was it increasing or decreasing speed? It seems to start out from rest and speed up or increase speed from there. So we can say that we were increasing speed. So now we can explain this with our evidence, reasoning, and claim. You can either use ideas of forces in Newton's second law to explain this, or the ideas of kinematics to explain this. I'm going to go with kinematics because I've already set myself up well for that. So we know the direction of the mass's motion is downwards and it's increasing speed. So we can start off with our fact of physics, or our evidence, that when an object increases speed, its acceleration is in the direction of motion. So that's going to be my evidence here. Then I can have my reasoning that since this hanging mass is moving downwards while increasing speed, I can then make my claim that my acceleration is going to be directed downwards for this hanging mass. So the hanging mass's acceleration is directed downwards is going to be my claim. So now let's move into part E. Let's move into part E. We're going to create a Newton's second law equation for my cart M1 after it is released. As you can see here, I'm breaking this down into as easy to digest pieces as possible. As you get better with the modified Atwood machine and even the regular Atwood machine, you pretty much do this whole step of making the Newton's second law equations and then combine them in one step. But we're kind of just breaking it down because we're learning it as we go here. So for the cart, let me remind you of what the free body diagram looks like for that. So what we had for that one, we had FG going straight downwards, you had FN going straight upwards, and you had FT to the right. So with this, we figured out based on our facts from acceleration from kinematics, and now with our forces, that our acceleration was directed to the right. So with Newton's second law, F net equals ma, our F net here is going to start off with right forces. So I'm going to have here right forces minus the left forces, which do not exist here. So minus left forces are equal to ma. So our right force here, that's Ft. That comes straight from the free body diagram again. Left forces don't exist, so it's just going to be equal to ma. And my mass here, this is going to be important, is going to be m1 times my acceleration a. So that's going to be my Newton's second law equation for my cart. I'm just going to keep it like that for now. Keep this in mind because we're going to combine it with the Newton's second law equation for the mass m2 in a few parts here. So let's move into making the Newton's second law equation for my hanging mass m2. Alright, so for the hanging mass m2, remind you of what this free body diagram looks like once more. You had FG going downwards, and you had FT going upwards. And we figured out that the acceleration was directed downwards. So Newton's second law again, F net equals ma. My F net for this situation is going to start off with my down forces, because again, we start off with the direction of acceleration. So down forces minus up forces are equal to ma. So for this situation, my down force, that's Fg. My up force, that's Ft, is equal to my mass here, that's m2 times a. Go one step further, we know Fg is mg, so that's going to end up being m2 times g minus Ft is equal to m2a. So now we have both our equations here for Newton's second law for both these objects. We're going to combine them in the next part in order to then find my acceleration of the system. So let's move into part E. Alright, so in part E, we're going to combine my Newton's second law equations. So essentially just add them together. So what we had here is the cart first, and my cart, that was going to be just Ft is equal to m1 times a. Then for the hanging mass, we had there m2g minus Ft is equal to m2 times a here. So what we're going to do with this is just add them together. So essentially just add this together here, Ft plus a negative Ft. My tension is going to end up canceling out. I'm going to end up bringing down here m2g. Then you have m1a plus m2a. Acceleration is the same for the system, so this is just like add in 2x plus 3x. What we have here is going to just be m1 plus m2 times my acceleration for the system here. All right, so the last part here is getting a by itself, then plugging in what we have, and then we're going to get the acceleration for this system. So what's attached to my acceleration a? It's going to be m1 plus m2. So I'm going to divide this out on both sides of the equation. Cancel out over here. On the left side, I'm going to be left with m2 times g over m1 plus m2. Do not divide out, or do not cancel out my mass m2 here. You're not going to end up being correct. So we'll bring this up here. my acceleration is equal to m2 times g over m1 plus m2. So that's my acceleration there. It's like if I had to derive for my acceleration in a part 2 or an FRQ of the AP exam, that's what I would have done. But you can see how it's broken down to get to this point. Now we're going to plug in our numbers, because say if this was a lab or you want to go to the simulation that I have in the description down below there, you can then actually test out what we have here. But more or less for like lab purposes, you can end up testing this out. So my acceleration is going to be equal to my mass m2 was the hanging mass, and it says that the hanging mass was 0.3 kilograms. That is multiplied by g. We know g is 10 newtons per kilogram, or some teachers will just use it as 10 meters per second, same exact thing. On the bottom there we had our masses. M1 was the cart, that's 0.25 kilograms plus 0.3 kilograms for the mass of the hanging mass there. Then you're just going to plug this in to your calculator. There on top you have 0.3 times 10. That's going to be 3 over 0.25 plus 0.3. And you're going to have here 3 divided by 0.55 is going to give me an acceleration for this system of 5.45. So 5.45 meters per second. To again remind us that acceleration is the change in speed for an object every second. So that's going to end up being our final answer there. That's the acceleration of the system. And if you want to test that out in the classroom or something like that, you're going to get close to that answer there. So let's now move into our last part, getting the tension in the strain. Alright, so in the last part of this example and of the video, we're going to calculate the tension of the strain that connects the two objects. So for this, I'm going to be able to use my acceleration that is for the entire system that I found in the previous part of this example, and I'm going to use one of my two Newton's second law equations that I created earlier. If I use the combined one, as you can see, tension cancel out, so I can't use that one. I have to use one of the two individual ones here. The one that sticks out to me as the easier one is going to be the Newton's second law equation that we created for the cart. If you recall, this equation is written out as Ft is equal to m1, the mass, times my acceleration of the system. And with this, why is this easier? I already have Ft isolated to one side of the equation. If I use the Newton's second law equation for the hanging mass, I have to do a little bit of algebra to get to this point. For this one, I'm going to just be able to plug in what I know, and it's a fairly easy math question from here. So for this, all I'm going to do now is plug in what I know. So again, why I can use either one of these, same rope or same strain, same tension. So I'm going to just plug in what I know. Ft equals my mass m1, which is the mass of the cart, and that was 0.25 kilograms, multiplied by my acceleration of the system, which was 5.45 meters per second. Alright, so then I'm just going to combine these two in my calculator and end up with my answer. And my answer is going to be the same for either way that I do this. If I did the hanging mass as well, you're going to get the same answer up to the hundredths place, just depending on how you rounded there before. And you're going to end up here with 1.36 newtons. So my Ft, my force of the strain on both these objects, is going to be 1.36 newtons. Alright, so that's my final answer here in the last part of the video. I hope this example was helpful, and see you guys in class.